Hello everybody and good morning. Today we're going to be starting the last section of chapter 14 on solids, liquids, and gases. And this last section focuses specifically on the behavior of gases. One of the things we need to understand is the main idea of this section, and that is gases respond to changes in three things, okay? They respond to changes in pressure, temperature, and volume. And they respond in predictable ways. So gases respond to changes in pressure, temperature, and volume in predictable ways. We're going to be looking in this section at two of the biggest ideas about gases and how they behave when there are changes in either pressure, temperature, or volume. Okay? Now, one thing we need to remember about a gas is that Pascal said a gas, because it is a fluid, exerts a pressure on surfaces of the container that it occupies. And remember, it also takes up the entire volume of the container it occupies. Keep that in mind too. So now what we're going to look at is an interesting way that gases respond to changes in pressure and volume. This particular law was discovered by a scientist named Robert Boyle. So today we call it Boyles Law. And it is a law. It's not just a principle, it's a law. If the temperature of a gas remains constant. Now, why are we doing this? Why are we letting the temperature remain constant? Remember, we've got three different variables right here. We can only change one variable at a time to see how it affects another variable. All right? Any other variables have to remain constant in order to see what happens with the two variables that you're looking at. So in this particular case, we're going to be focusing on volume and pressure, and we're going to keep the temperature of the gas constant. If the temperature of the gas remains constant, then as the volume of the gas decreases, the pressure will increase. Now, if you look at this picture right here, here is a cylindrical container with a piston on the top and a gas inside. If we make the volume bigger, the pressure exerted by the gas on the inside walls decreases because there's more volume for the little molecules to move around in, so there's not going to be as many collisions with the sides of the wall, and therefore less collisions, less pressure. So increase the decrease you decrease the pressure. But if you push the piston down and decrease the volume, that means there's not as much room for the molecules to move around in, and there's going to be a lot more collisions between the walls and the particles. So, more collisions, a greater pressure is obtained. So, volume decrease, pressure increase. So this is sort of an inverse relationship, guys. If you increase the volume, you'll decrease the pressure because you get fewer collisions. If you decrease the volume, you're going to increase the pressure. So they do just the opposite of each other, okay? When one gets bigger, the other gets smaller, and vice versa. In fact, if we were to graph this, the graph would look like this. As the volume, down here on the bottom, as the volume increases, the pressure is getting smaller and smaller. But if you decrease the volume, you increase the pressure. So going this way along the curve, if you go up the curve, you're increasing the pressure, but at the same time, you're decreasing the volume, okay? If you come this way along the curve, you're decreasing the pressure while you increase the volume, okay? All right, and please remember, as this is taking place, we are keeping the temperature of the gas constant. We're not changing the temperature, because if we did that, if that happened, you really couldn't see, is it the temperature changing that affects this, or is it just one of these affecting the other? So you have to keep all the other variables constant when you're looking at just two of them. Keep that in mind. Now, this is why the fact that the volume increases as the pressure decreases is why a helium balloon expands as it rises through the atmosphere. The atmospheric pressure that acts on the outside of the balloon keeps the balloon from getting bigger if you stay at the same location, okay? So the pressure inside and the pressure outside are the same. But if you change the location of the balloon, for example, you take it to somewhere where there's a higher altitude. Now, most of you realize that as you go up through our atmosphere, the atmospheric pressure decreases because there's less and less layers of atmosphere above you the higher you go. So atmospheric pressure decreases. In fact, this balloon starts out in San Diego, it says right here, and they're going to take it to Denver. So as you're traveling to Denver and your altitude increases, in fact, they show you right here, the difference in altitude between San Diego and Denver is a little over 5,000 feet. So the outside pressure pushing in on the balloon decreases. It gets smaller, okay? Therefore, the inside pressure, which hasn't changed, it's bigger, and it can push the balloon outward. It makes it expand. So the pressure difference, the increased pressure from here to here, makes the balloon expand, okay? Now, eventually, the balloon expands to the point where it pops. If you're an environmentalist, this is one of the things you know that's kind of bad, because people let balloons go in the atmosphere all the time, and then they get high enough, they pop, they fall back to Earth, many times in the ocean, and sea life in the ocean can mistake these popped balloons for squid and jellyfish, and many of them eat those, and so then they eat the balloons, which are not digestible, and the balloons get stuck in their digestive tracts, and it eventually kills the sea creatures, which of course we don't like, which is why it's not a good idea to release balloons into the atmosphere. But people do it anyway. Now, there is a, there is a formula that we can use for Boyles Law. Swallowed wrong. To show the relationship between the pressure and the volume. And here it is right here. If you look at the balloon at one location, the product of its pressure and volume should equal the product of its pressure and volume at any other location. So if one of these changes, it changes the other. This one will increase, the other will decrease. That way the new product will still be equal to the old product. So for example, if you had 5 and 10 here, that's 50. And maybe this one decreases to 2, this one increases to 25. 2 times 25 is still 50. So you get a relationship there. One increases, the other will decrease, or vice versa, so that the two products are still the same value. Now, how can we use this formula? Well, let's look at a little practice example here. Suppose we have a weather balloon, and it contains a volume of 100 liters. Always underline your information, and then we'll identify it. This helium balloon is released from sea level. So this is where we know it is initially. So let's call this the initial velocity. It's released at sea level, so that's going to be the location of our initial state. So, initial velocity of 100 liters, and it says the pressure where it's released is 100 kilopascals. So this is going to be the initial pressure. And then the balloon is going to obviously float upward because the helium is lighter than the air or less dense than the air around it, so it will float upward. And as the pressure decreases around the balloon will expand until it reaches an altitude where the pressure is 43 kilopascals, okay? And we want to know what will be the new volume of the balloon. Well, this new location is where we have our final state. So at sea level was our initial state, and at the new altitude is our final state. So this is going to be the final pressure. Remember, pascals pressure, liters volume. We want to know what will be the new volume. So we want to find out what is VF. Okay? Now, oh, hang on. They're making announcements. Just a moment, please. All right, I think she's done. Okay, so now let's think about what's going on. Look and see. Notice what's happening to the pressure. Initially, it was 101 kilopascals. Now it's 43 kilopascals. So the pressure has decreased. Well, according to our graph, if we have a decrease in pressure, we should see an increase in the volume. Okay, so the pressure's decreasing, the volume should increase. So when we find the volume, it should be greater than the initial, which was 100. All right, that's what we hope to see if we do this right. So let's start out by first writing down our formula. We've got the initial pressure times the initial volume equals the final pressure times the final volume. Now, I like to underline what I'm looking for, and I'll show you why in a moment. We're looking for the final volume. Here it is, so I'm going to underline it. That's what we're looking for, okay? Now, what we need to do is isolate that variable. You know, like you would say x equals blah, 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 blah. That's kind of what we want to do here. We want to isolate it. That means we need to get rid of the pressure to the other side. But how do we do that? Okay, algebra trick, math trick. If you're multiplying what you're looking for by something else, you do the opposite with that something else on the other side. Here, we're multiplying by PF. The opposite is divide, so what we're going to do is we're going to divide both sides by PF, because the opposite of multiply is divide. So now that gets rid of PF on that side and leaves it on this side, and we've isolated VF. So basically, we now have VF by itself equals PI VI over PF. Now that wasn't too difficult, is it? In fact, on any one of these, whichever one you underline, you're going to divide by the other one to the other side, because all of these are multiplication, aren't they? So if you were looking for PI, you'd take the VI and divide it on the other side. If you were looking for PF, you would take the VF and divide it to the other side, because the opposite of multiply is divide, okay? Now, we've got our working formula, so let's plug and chug. We've got 100 kilopascals, 101, kilopascals for the initial pressure, and for the initial volume, 100 liters. That's a decimal, not a comma. And our final pressure is going to be 43.0 kilopascals. Okay? Now, if we stick that into our calculator, and I don't know if you can see that, so I'm gonna do it this way. All right, we got it. There we go. So we get 101 times 100 liters divided by 43 kilopascals. And look, we get 200, and I would just simply take the 0.88 and round the 4 up to a 5. Just say 235, because 234.88 is closer to 235 than it is to 234. So 235. But 235 what? Well, look back over here. Let's look at our units. We're dividing kilopascals by kilopascals. That cancels. What we're left with is liters. So this is 235 liters of volume. Now look, what did we say we should see? We said we have a decrease in pressure, so we should have a corresponding increase in volume. We had 100, now we have 235. Yep, we had an increase. So 235 liters is going to be the new volume of the balloon. So that means it's going to be about 2.4 times bigger than it was before. Okay, it's really expanded. All right, if the elastic can handle it, it'll be fine. But if it stretches the elastic too far, boom, it'll pop and fall. Okay. All right, now we're going to be practicing some of these later on. So keep this handy. Never throw away your notes, guys. You're going to need your notes like nobody's business. So never throw away notes. Keep them handy, okay? All right, talk to you tomorrow. Bye-bye.